My name is Peter Kjeldsen, and I'm a professor at the Department of Environmental Engineering here at Technical University of Denmark. I'd like to introduce to you the biocover technology, which is used to reduce greenhouse gas emissions from old landfills. Landfills containing organic waste produce a lot of methane, which can be emitted to the atmosphere and is a very important contribution to global warming. We can use landfill gas for energy purposes, but there might be problems with that. Most landfill gas on a global scale is actually directly emitted to the atmosphere. It's only on a selected landfills that this energy utilization takes place. Experiments have documented that the methane in landfill gas can be oxidized by microbes in covers and biofilter installations in the landfill. And we have seen very high oxidation rates in the covers and in biofilters. So this process can be the basis for developing what we call a biocover technology to reduce the methane emissions. This methane oxidation process has, over the years at DTU, been studied a lot in simple batch experiments, more advanced column experiments, which gave us a lot of information about environmental factors governing how fast the methane oxidation rate takes place. And this basic understanding of the processes has now been developed into implementation of full-scale biocover systems on landfills in Denmark. This is from the Kjeldsen landfill, and I will actually use the Kjeldsen case, to show you how we work with implementation of biocovers, how we plan, how we construct, and how we document efficiency for the methane removal. The Kjeldsen case is 1 out of 3 we have worked with. And we work together with the company Landfills, together with the local landfill owner to get implementation of this biocover at the Kjeldsen landfill. We developed a project protocol with 6 steps which you have to go through. The first step is the initial characterization of the landfill. We did that and we found out how big the landfill cell we worked on were, and what kind of the volumes of waste and what kind of waste was contained. We also learned that it was covered with a lot of soils on top of the landfill, except on the slopes. Next step is the baseline study of methane emissions, where we use different methods and tools to evaluate how big spatial variability there are in emissions from one place to another. And these activities showed that the baseline showed, this baseline study showed that emissions only happened at the slopes. However, the most important part of the baseline study is to measure the whole methane emissions from the whole landfill cell using the dynamic tracer dispersion method. I won't have time to go into the details of this, but you can see it on another video talk on our website made by Charlotte Scholz, who's one of my colleagues. This slide shows the result of the measured emissions. We can see that the emissions before we installed any biocover was in the order of 4 to 6 kilograms methane per hour, and that was then the basis for working further. Next step is to find good available materials which can oxidize, and here the local compost samples produced by the waste company Kjeldsen was tested in the lab experiments we have developed, and we saw that the methane oxidation capacity was optimized by combining 2 different composts, and about nearly 4,000 cubic meters of this compost were produced to be put into the landfill, the biocover technology. So based on the result of the reported methane emission, where it was, and that was on the slopes, and the whole emission in kilograms per hour, and the compost ability to oxidize the methane, we planned and established the full-scale biocover system. Here we can see a sectional view of the landfill with the waste in here. We covered with a gas-impermeable soil and installed trenches which routed the gas up to the installed biofilters on top of the landfill where the methane oxidation took place. So the construction process turned an old uncontrolled landfill, more or less, here's an aerial photo of that, into an engineered biocover system consisting of covered slopes, trenches, and biocover filters placed on top of the landfill. Here we can see a picture from just after the installation, taken just after it was made, where we can see the biocover installations here. The fifth stage is to monitor the gas emissions from the biocover using the same method as we used in the baseline study. Here we can see the result of the total measurements, and we can see after a little bit of repairing of the system, we got down to about 1 kilo per methane per hour, and that led to a measured efficiency of 83% of reduced methane emissions from the place. Last step is the economical analysis based on the establishment cost and the running cost over a 30-year period, and compared to how much methane is being mitigated, is being reduced over the same 30-year period, we come up with a mitigation cost of about 22 euros per ton CO2 equivalents, which is on a lower range compared to other mitigation methods used in the Danish society. So finally, I want to say something about the future of the biocover technology. Based on the success of the Clinton case and the low mitigation cost, the Danish government has initiated a program where they want to establish biocover systems on 100 landfills. And they have set aside about 185 million kroner over the next 4 years to do that. However, we are good at not disposing of organic waste at landfills in Denmark at the moment. So the future lies not in Denmark, but in the rest of the world, where landfilling of organic waste is still the most used managing options in a lot of countries. So significant releases of methane from thousands of landfills around the world will happen the next centuries. And the biocover technology could in many cases be a cost-efficient option for greenhouse gas emissions at these landfills. Thank you for your attention.